Dr. Zaritzky, we are ready to start.
Okay.
Hello.
Hello, good evening in China and good morning in Argentina. Thank you for joining us today. Hello, everyone. Welcome to our second joint webinar organized by the Engineering Academies of China and Argentina on food research and technology. You are pleased to share this activity with you. And the topic of this second joint webinar is green food change, sustainable and biodegradable packaging for food and recovery of food waste from the food industry case studies. Thank you for taking the time to join us. My name is Noemí Zaritzky. I will be the host in this session. And let me introduce to the engineer Oscar Viñard. He is the president of the Academy of Engineering in Argentina, and he will give us some introductory remarks about the joint project between both engineering academies. Please, Engineer Viñard.
Good evening, good morning. I'm very happy to open our second webinar on green food chains, sustainable and biodegradable packaging for food and recovery of waste from the food industry case studies. I'm sure it will be as successful as our first one on probiotics, prebiotics, and symbiotics. Data published recently in Argentina on the country external trade show that China is Argentina's second largest trade partner, second to Brazil, our neighbor and member of Mercosur, a regional free trade zone. Exports from Argentina to China are mainly food products, being these key exports, and therefore reinforcing the importance of our webinars that were based on food technology and engineering. Hopefully, the relation between our academies will keep growing, benefiting both countries and originating many new joint projects. Thank you very much for being here.
Thank you, Engineer Viñard. And I invite now Dr. Liu Chang, Deputy Director General, Department of International Cooperation of the China Academy of Engineering, to talk about our joint project and the importance of this joint webinar. Please, Dr. Liu Chang.
Thank you. Good morning, good evening. So respected President Oscar Viñard, it's great to see you again right here. And distinguished Dr. Zaritzky, thank you for all your efforts and for being the host for the first session. Distinguished experts and scholars from China and Argentina, dear colleagues, it is a great pleasure to gather online with experts and scholars from both countries to kick off the second online seminar of the China-Argentina joint research on food nutrition, health processing, and storage. So first of all, on behalf of the Chinese Academy of Engineering, I would like to extend my warm congratulations on the convening of the seminar and also express my gratitude, sincere gratitude, to all the Argentine experts, Chinese experts, as well as the staff of the organizers, namely Jiangnan University and CIDCA. While under the framework of CAE and ANI cooperative agreement, the cooperation in food science and technology between the two sides has been advancing steadily. And this series of seminars is an important implication measure of the joint research program launched by the two academies. Well, when we now look back at the first seminar held on September the 29th, we focused on the theme of food nutrition, probiotics, prebiotics, and symbiotics, and achieved fruitful discussion results. Argentine experts shared their research on the development of bioactive substances in artisanal fermented foods and the potential application of bifidobacterial, and introduced the current situation of probiotic and prebiotic dairy products in Argentine market, as well as nutrition improvement initiatives of enterprises. And those experts on the China side delivered in-depth presentations on topics such as the interaction between dietary polysaccharides and gut microbiota, and the mechanism of bifidobacterial associated with breastfeeding in alleviating neonatal it's difficult. Hyperbilirubinemia and inhibiting colorectal tumorigenesis in mice. So during the discussion section last time, experts from both countries or both academies or both sides conducted in-depth exchange on technical difficulties and application scenarios. Thus laying a solid foundation for future communication and exchange. And today, in the second seminar, we're going to focus on the theme of green food chains, with key discussions centered on two core topics, which are sustainable and biodegradable food packaging and the recycling and the utilization of food industry waste. This not only responds to the green development needs of the food industry in both countries, but also serves as a precise extension of our previous cooperation directions, aligning with the practical demands of the food industries of China and Argentina. Following the successful format of alternating presentations, Chinese experts will share the research today on green packaging and related regulations and standards, and the valorization of food byproducts, and the secondary value creation of grain resources. And our Argentine experts today will present their achievements in bioplastics for sustainable packaging, sustainable micro and nano composite materials derived from agro-industrial byproducts and their applications, as well as the application of food waste vectorization in the remediation of contaminated water. I look forward to all experts conducting in-depth discussions based on practical experience, which will not only spark sparks of technological innovation, but also identify cooperation entry points that can be advanced rapidly, so that the outcomes of the seminar can truly serve the industrial development of both sides. Going forward, the two academies will continue to build such pragmatic exchange platforms, promoting practical cooperation in the field of food science and technology between China and Argentina, and facilitating the translation of research outcomes and research findings into real-world applications. With this being said, finally, I wish the seminar a great success. Thank you all.
Thank you very much. And we are waiting for the introduction of the speakers from China. Can you please introduce your speakers?
Okay, thank you. Good morning and evening. I'm Yunfei Xie, Deputy Dean of the School of Science and Technology at Jiangnan University. On behalf of Jiangnan University, it's my great honor to introduce our distinguished speakers. They are Dr. Weirong Yao, Dr. Song Gao, both from the School of Science and Technology, Jiangnan University, and Dr. Rui Liu, from the Institute of Food and Nutrition Development, Ministry of Agriculture and Rural Affairs, China. And the last is Dr. Yong Yang from Butcher China Holding Company Limited. We are honored to have them share their experts with us today. Thank you.
Thank you very much. We will now introduce the speakers from Argentina. Please, Margarita, can you share with us the video?
So
放视频，把你报个视频。
不是，他其实他那边的真的会。
应该是。
Yes, can you start the video? We are not hearing, I think.
Welcome to our second joint webinar on food research and technology, green food chains, sustainable and biodegradable packaging for food, and recovery of waste from the food industry, case studies. This webinar is organized by the Chinese Academy of Engineering and the National Academy of Engineering in Argentina. It's my great pleasure to introduce the speakers from Argentina who will give their lectures today. Our first speaker is Dr. Celina Bernal. The title of her presentation is Bioplastic for Sustainable Packaging. Celina Bernal is Associate Professor of Material Science in the Department of Mechanical Engineering at the University of Buenos Aires. She is Principal Researcher and member of the Qualification and Promotion Main Tribunal at the National Research Council of Argentina, CONICET. From 2021 to 2025, she was head of the Institute of Technology in Polymers and Nanotechnology, which depends on the University of Buenos Aires and CONICET. In April 2025, she was elected as a member of the National Academy of Engineering of Argentina. Her current research focuses on the mechanical behavior, fracture, and failure mechanism of polymers, blends, and composites, polymer processing, and the design of multifunctional composite and environmentally friendly polymer-based materials. She has authored over 85 peer-reviewed journal articles, contributed 8 book chapters, and presented more than 170 papers at scientific conferences. Our second speaker is Dr. María Alejandra García. The title of her presentation is Sustainable Micro and Nanocomposite Materials Derived from Agro-Industrial Byproducts and Their Applications. María Alejandra García is Principal Researcher at the National Research Council of Argentina, CONICET. She's Associate Professor of Instrumental Analytical Chemistry Material Science in the Department of Chemistry at the National University of La Plata. She received the L'Oréal UNESCO National Award Mention in 2020 and in September 2023 the Conex Award Diploma of Merit in the discipline of Agrarian and Food Sciences. She has authored 115 peer-reviewed journal articles, contributed 20 book chapters, and presented more than 200 papers at scientific conferences. She holds 4 granted patents. Her research focuses on the development and characterization of biodegradable materials for food packaging, the development of nutritionally differentiated foods, and the valorization of agro-industrial byproducts. Regarding human resource training, she has supervised 6 doctoral theses and co-supervises 2 others, all from the University of La Plata. She currently supervises 3 doctoral theses at the Faculty of Exact Science at the University of La Plata. The third speaker from Argentina is Dr. Noemí Zaritzky. The title of her presentation is Food Waste Valorization for the Remediation of Contaminated Water. Noemí Zaritzky is chemical engineer from the Faculty of Engineering, University of La Plata, Argentina, doctor in chemical sciences from the University of Buenos Aires, full professor of fluid dynamics and of heat and mass transfer in the Chemical Engineering Department, Faculty of Engineering, University of La Plata, emeritus professor, superior researcher at the National Scientific and Technological Research Council, CONICET. She was director of the Center of Research and Development in Food Science and Technology between 2003 and 2016. Titular member of the Buenos Aires Academy of Engineering, of the National Academy of Engineering in Argentina, and of the National Academy of Exact Physical and Natural Sciences. Full member of the World Academy of Science for the Advances of Science, TWAS. She has received many national and international awards. He was director and co-director of 36 PhD theses, author of 278 research articles published in peer-reviewed international journals of high impact, 55 book chapters, 670 presentations in scientific conferences, 6 granted patents. She has given more than 100 guest lectures and invited talks at national and international conferences. Specialty Chief Editor in the journal Frontiers in Food Science and Technology. Her main research lines are mathematical modeling and computing simulation of heat and mass transfer, food processing and preservation, physical properties of food, viscoelasticity, wastewater treatments, biopolymers, food waste valorization.
Okay. Continuing with the webinar, we will begin with the first speaker. The first speaker is Dr. Weirong Zhao, and the title of his conference is Research on Green Packaging, Packaging Waste, and Related Regulation and Standards.
Hello, everyone. I'm Yao Weilong from the School of Food Science and Technology, Jiangnan University. My topic is research on green packaging, packaging waste, and related regulations and standards. Today, I will mainly introduce three parts. First is the core principles of green packaging. Second is the related regulations and standards. The third is the most important, our research on green packaging. Currently, there was a harsh reality in the earth, which was plastic pollution, and it was reported that the plastic waste reaches 7 billion tons, and among them, there was 30–60% from packaging. Also, there was a dual crisis, that is packaging and food waste. 1/3 of the world's food is ultimately discarded, and these waste foods emit 8% to 10% of greenhouse gases. To solve these two difficult problems is green packaging. One solution is to end plastic pollution at its source by replacing traditional plastic with materials that can return to nature from the source. Another one is protecting food by advanced packaging, actively extend the lifespan of food and reduce the food waste. It was expected to reduce 3.3 million tons of carbon emissions annually. So, what is green packaging, which could be summarized as 3R1D? First is reduce. This is the most fundamental principle. It's about minimizing material usage from the very beginning and fighting against excessive, unnecessary packaging. Second is reuse. This is to design packaging that can have a second, third, or even fourth life, significantly extending its life cycle before it becomes waste. Third is recycle. When packaging can no longer be reused, it should be designed for easy collection and reprocessing into new valuable products. Finally is degradable. For specific applications, the ideal packaging is which could be broken down and returned to nature, minimizing long-term pollution. There is a clear global trend towards strict green packaging rules. Key themes are emerging everywhere, banning problematic single-use plastics and implementing extended producer responsibility, where companies are financially responsible for the waste what they create, such as the European Union has a comprehensive packaging and waste regulation. Canada has moved forward with a single-use plastics prohibition, and major economies like Japan, the USA, Brazil, and China all have specific regulations to promote green packaging. For example, the US landmark Packaging and Packaging Waste Regulation. It sets a new global benchmark to redefine how packaging is designed, used, and recycled. The core requirements, including packaging reduction targets, design for recycling, reuse target, recycled content requirements, single-use packaging restrictions, restriction of hazard like bisphenol A, extended producer responsibility. Its key target is to reduce 20% plastic packaging by 2040. In China, The renewed law of agriculture product quality and safety in 2022. There are two terms, especially on packaging and labeling for agri-food. To act them, two national standards on green packaging were set up, targeted to fresh edible agri-food. One is GB 43284 in the year of 2023. It is to prevent excessive packaging. And another is GBT 46685 in the year of 2025. It is about scientific packaging technology. Both the standards have an administrative measure for the packaging and labeling of agricultural food products. Earlier in 2006, is being ready to change it or revised. The packaging part just including the national standard GBT 46685 and later especially focus on labeling requirement will be set up agriculture industrial standard. In these future tasks, our group in Jiangnan University are the main technical chief writer. Now let's have a look about our research on green packaging in Jiangnan University. The key work is to study the quality prediction model for packaged agriculture products. Another tool is about active and intelligent packaging technology. During our study, 3 types of fresh cut vegetables was packaged by 4 kinds of packaging film with different OTR value. The results showed that when the OTR value of packaging films decreased, their share life extended. The most longest share life is from fresh cut lettuce, cucumbers. Packaged by the film with the lowest OTR value, the share life could be delayed to 12 days. Based on the exchange of oxygen and carbon dioxide from fresh cut vegetables, close model of the main sporadic organisms, which was artificially inoculated Pseudomonas fluorescens, and the OTR of packaged film. We developed an equation by coupling with them, 3. The results showed for each specific product, there is optimal OTR to maintain freshness and quality, and demonstrated good accuracy. Then we designed a model with the prediction equation. The software could predict the share life of packaged each kind of vegetable and also their mixture. It means that we could set 2 of 3 key facts, including the kind or its value OTR of film, a certain fresh cut vegetable, or a certain share life. Then the rest 1 factor could be predicted. Now let's follow the procedure of demo. I'm sorry, the demo is written in Chinese, but there are English letters. In the future, based on the expected duration of storage, transportation, and sales for a certain batch of fresh cut vegetables, the most economical packaging film with certain breathability can be selected. We trust this model will help the vegetable producer to package their product to maintain their expected share life. Next is our work on active packaging, where the package itself plays a role in preservation. A double-layer film was used by electrospinning technique to create a nanofiber layer with polylactic acid and gelatin as the outer layer, and the inner layer were infused with natural antibacterial agents like eugenol, derived from cloves, a kind of flour. The films are fully biodegradable. During packaging, this film could slowly release the active ingredients and create a protective gas environment. We demonstrated their higher antibacterial rate against common pathogens like E. coli. Then we used this active film to package grape, cucumber, or peach, all showing a significantly enhanced shelf life, more than 30% to 50%. Another example of active packaging is inspired by nature's lotus leaf. We call it as bionic antibacterial film. Firstly, we extract the essential oil from lotus leaf, screened a kind of fermentation product, polylysine, and combined a synergistic action. This active combination was embedded in a gelatin polymer to produce active film. Then the surface of lotus leaf was imprinted onto its surface, and it obtained exactly the same rough dot structure like the surface of lotus leaf. It could mimic the hydrophobic self-cleaning properties of the lotus leaf. The film achieves a sterilization rate of over 97% against common sporage bacteria. The microstructure that repairs water droplets, just like lotus leaf, keeping the package film separated each other and not to be contaminated. This superior preservation capability leads to extension the shelf life with 30% to 50% for fresh cherry. The final part of my topic is intelligent packaging. Consumers always hope to know at a glance the freshness of packaged food or whether it is still safe to eat. So we want to develop smart packaging that can display the real-time status of food. A two-layer film was made by Conzen. The inner layer contained pH-responsive indicators. As a sign, during storage or transfer, the packaged fish of pork spoils. It releases flight compounds with ammonia. Result the color change from pink to white and further to green or blue, directly collected with flesh, stale flesh, and spoiled solid levels. So it could provide a clear, real-time visual signal to freshness of food. Our another freshness indicator is a natural biomimetic material. It mimics color change in spawning shrimp. The key ingredient is astaxanthin, the natural pigment that makes shrimp red. The indicator mechanism is based on the change in protein structure. In a fresh environment, the indicator protein has a planar structure and appears blue. As microbes glow and the environment changes, the protein twists, causing a visible color shift to red. This provides a very clear visual cue of spoilage. We have successfully applied this indicator in both ink and label formats, making it a highly practical solution for pork and tofu packaging. Also directly correlates with fresh, still fresh, and spoiled solid levels. Thank you.
Okay, thank you very much for the presentation, and we are going to our fresh presentation from Argentina. It will be delivered by Dr. Celina Bernal, and the title is Bioplastics for Sustainable Packaging. Please, Margarita.
First, I want to thank the Academy of Engineering of China and the Academy of Engineering of Argentina for giving me the opportunity to make this presentation. Then, I'll talk about bioplastics for sustainable packaging, and particularly, I'll present some results obtained at the Institute of Technology in Polymers and Nanotechnology of the Engineering Faculty of the University of Buenos Aires and the National Research Council of Argentina. At the beginning, I will present the scenario of bioplastics in Argentina. Then, I will show some results about the development of bioplastics, which are bio-based and also biodegradable. And finally, I will show some concluding remarks related to these results. The use of plastics in Argentina are mainly related to packaging, construction, electricity and electronics, and also in the automotive industry. The plastics are imported from Brazil, United States, China, and also from other countries. This information was obtained from the Argentine Chamber of the Plastics Industry. More specifically, regarding the use of bioplastics, 30% of the surveyed companies are using these types of plastics. PLA, Matter B, biopolyethylene, Ingeo, and PHB are the most used bioplastics. They come from Germany, Italy, Brazil, Spain, United States, and Australia. This information was taken from the Bioplastics Initiative of the Argentine Ministry of Economics. These bioplastics are used especially for packaging, laminates, bags, 3D filaments for additive manufacturing, mulch films, cutlery, master batches, and other uses. And in the economical sectors of textiles, agriculture, in a very high extent in food packaging, in gastronomy, and 3D printing. There are many limitations and needs, particularly lack of local producers, differences in cost of biopellets in comparison with conventional plastics, the need of continuous access of raw materials, the lack of diversity of providers, and, of course, poor properties of bioplastics compared to conventional plastic. The main bioplastic required are polylactic acid, those similar to polypropylene or polyethylene, and bio-oriented polypropylene. And there are also other bioplastics required, such as those suitable for food contact. In Argentina, there are many research centers working in the development of bioplastics, particularly of biopolymers in the form of biofilms, and also adhesives and other developments. After the brief introduction about the situation of bioplastics in Argentina, I present the results about the bio-based and biodegradable films based on starch and natural extracts. These developments were carried out in collaboration with the Exacts and Natural Sciences Faculty of the University of Buenos Aires. We obtained cassava starch-based films with different concentrations of yerba mate extract. These films presented significant antioxidant capacity from the incorporation of the extracts, and the surface of the films was hydrophobic as revealed from surface roughness, contact angle, water vapor permeability, and water content results. We also found important improvements in the elasticity of the films and a shift to lower temperatures of the transitions associated with the glycerol-rich and starch-rich phases. We developed thermal analysis, structural and chemical analysis also. We studied the stability in different solutions and the disintegration behavior. We found a plasticizing effect of yerba mate extract on the starch glycerol films, as you can observe in the stress strain curves on the right. We also found a decrease of the film's disintegration time in compost in laboratory conditions and an increase of stability in acidic and alkaline media. So we observed that the extract is an attractive additive for starch-based films, which can be used for packaging or coating. We also tried another natural extract, such as green tea and basil, in the same type of films, and we found antioxidant activity in the films containing the extracts, changes in the color when exposed to different pH, fast films disintegration in compost, reduced films water vapor permeability, but also keeping the flexibility of the films, excellent thermal properties, and again a plasticizing effect of the extract. This was confirmed from crystalline structure, thermal degradation, and tensile property results. After the previous results, we tried also the use of silver nanoparticles which were synthesized with starch and yerba mate, and the films were obtained now with a more scalable processing technique such as extrusion and subsequent compression molding. The spherical nanoparticles were obtained after the green synthesis, as you can see in the scanning electron microscopy micrograph, and the nanoparticles had excellent adhesion with the matrix. They also promoted a very important reinforcing effect because the nanocomposites exhibited higher stiffness and tensile strengths than thermoplastic starch, as you can clearly see in the stress strain curves. The green curve is related to the nanocomposites. All materials disintegrated after 4 weeks of burial and resulted thermally stable up to 240 degrees centigrade. So these new films were also promising for packaging. After the previous results, we also developed biodegradable and actively layered nanocomposites from 2 cassava starch-based films. One layer was composed of a starch yerba mate extract film, and the other was a starch titanium dioxide nanocomposite. The bilayer material presented excellent interlayer compatibility from the use of the same starch in both matrices. The bilayer also displayed activity against different pathogens and improvements in mechanical strengths and water vapor permeability. The films presented antioxidant activity and greater deformation due to the layer with the natural extracts, as you can see comparing the blue and the green curves, and the disintegration in vegetable compost was almost complete in 2 weeks. Another project was related to the development of PLA films. We obtained nanocomposite films based on polylactic acid and bacterial nanocellulose. The films were prepared by solvent casting, and native unacetylated bacterial nanocellulose was used. It was found that acetylation improved nanofibers dispersions in the matrix, increasing transparency and mechanical properties of the nanocomposites. We also found remarkable increases in stiffness without sacrificing tensile strength nor water vapor permeability. In collaboration with the University of Coruña, Spain, we also developed biodegradable films based on PLA blends. These films were obtained by cast extrusion, and we analyzed the effect of the processing conditions on the tensile and fracture behavior through changes of the extrusion rolling speeds. The films were completely ductile under tensile loading, but we've observed differences in the film's fracture behavior, which can be correlated with the processing-induced morphology. You can see on the left the scanning electron microscopy images from the different films obtained. In another project, we prepared PLA nanocomposite films reinforced with lignin nanoparticles. We used both pristine lignin and also chemically modified nanoparticles. We found that all lignin nanoparticles conferred UV blocking, antioxidant, and bacterial properties to the films, and chemically modified particles partially reduced some properties, but also improved better or lead to better nanoparticles dispersion. It was evidence from the better ductility and the better aesthetic quality. For example, the characteristic dark color of lignin films was reduced. In migration tests and disintegration assays, the films prepared with nanoparticles presented similar behavior to neat PLA. More recently, in collaboration with the University of Perugia, Italy, we also obtained nanocomposite films of PLA and nanocelluloses. We use both bacterial and vegetal nanocelluloses. The materials were processed by melt compounding using both extensive mixing and extrusion. In order to avoid or limit the irreversible aggregation of the nanocellulose after drying, we used three different strategies for the incorporation of the filler into the polymer. One was the reference, and it was a direct addition of dried and milled nanocellulose into the processing machine. The other strategy was the use of PLA nanocellulose master batches obtained by solvent casting before the incorporation of the filler into the polymer, and the other strategy was the use of the same type of master batch but using acetylated nanocelluloses. We observed that the use of master batch was very beneficial for the dispersion of nanocellulose in the polymer matrix. So optical, thermal, and barrier properties were significantly improved. Hence, the master batch approach effectively minimized nanocellulose aggregation or ornification, and is a good strategy to enhance filler dispersion in this type of composites, particularly processed by conventional thermoplastic processing techniques, which is really important for industrial applications of this type of fibroplastics. From the results already presented, we can say that we obtain bio-based and biodegradable polymers and nanocomposites with functional properties. We made significant progress on the use of conventional processing techniques for bioplastics. And finally, we observed that industrial scale processing is still needed to properly use bioplastics for different applications. Finally, I want to talk about the location and the theme of the Institute of Technology in Polymers and Nanotechnology of the University of Buenos Aires and the National Research Council of Argentina. We are located at the city of Buenos Aires in the Middle East of Argentina. We have 3 campuses, one in Recoleta neighborhood, the other in San Telmo neighborhood, and the last in Núñez, in the university campus. This is a team of the institute. We have researchers, professors of the University of Buenos Aires, PhD students, some professionals for technical support, and finally, we also have undergraduate students. We have many collaborations with different universities and institutes from Argentina, from Buenos Aires also, and from other countries. The results presented in this talk were made in collaboration with the University of Perugia in Italy, the University of Coruña of Spain, Galicia, and of the Institute of Physics of Buenos Aires, from the University of Buenos Aires. Thank you very much for your attention and for inviting me to give this talk.
Okay, we are continuing with the next talk that will be delivered by Dr. Song Gao. The title is Mycotoxin Degradation and Valorization of Food Byproducts.
Good morning and evening, distinguished colleagues, honored guests, and experts in the food field. I'm an associated researcher from the School of Food Science and Technology at Jiangnan University. My primary research focus is on applying synthetic biology technologies to address food safety issues. In this presentation, I will introduce our research group's recent project, Mycotoxins Degradation and Valorization of Food Byproducts. The first part of my report is mycotoxins contaminations in grains and their mining fractions. Mycotoxins contaminations is a persistent threat restricting food security. Globally, about 25 of grains are contaminated by mycotoxins annually, and 2% lost their usability. In China, 31 million tons of grain are contaminated in the industrial chain each year, accounting for about 6.2% of China's annual grain output. Mycotoxins contaminating China's grain, including DON, AFTs, ZN, and FBs. Among all mycotoxins contaminations, aflatoxins have the highest toxicity. The overstandard rate of AFTs in peanuts in southern China reached 70.8. FB contaminations is the most widespread. The FB contamination rate in wheat-producing area, such as Anhui and Jiangsu province, reached 50. It is evident that mycotoxins contamination of grains is a long-term global concern. Contamination of grain by mycotoxins can also transfer to their byproducts. In China, 73.8 million tons of eatable byproducts are generated from grain processing each year, which are valuable grain resources. However, the average of the detection rate of mycotoxins in these byproducts is over 95.7%, leading to over 90% of the grain processing byproducts being used only in low-value applications. In recent years, the increase in extreme climate events has resulted in more grain being contaminated by mycotoxins and thus unable to be directly consumed. Therefore, our research focuses on how to achieve mycotoxins removal and value-added utilization of green byproducts. We selected two green byproducts as research objects. The first is corn steep liquor. CS is a byproduct of white corn processing. Per ton of corn produce 0.7 to 1.1 tons of CSL with 10% dry matter. The crude protein content in the dry matter of CSL is about 40%, and it also contains various organism compounds including lactic acid, glucose, and xylose with high nutritional value. However, corn is susceptible to aflatoxins contamination. Strains isolated from different ratio have different toxins producing compatibility, and those from high contamination area have significantly higher aflatoxins producing ability than those from low contamination areas. Strains from high contamination area can accumulate up to 142.1 ppm of toxins, which is more than 500 times than of low contamination area. Besides aflatoxins, ZN is also frequently detected in CSL. CSL is usually concentrated to 40% for storage and transportation. This concentration not only increases with viscosity, but also further raises mycotoxins levels, making it difficult to use in feed. To reduce mycotoxins contaminations in CSL, we attempt to inoculate food safety strains for fermentation. We verified that the food safety strain Aspergillus niger FS10 can grow in 10% CSL and decrease aflatoxins and ZN in CSL. After 96 hours of fermentation, the degradation rates of FB1, FB2, and ZN reached up to 93.8%, 68.9%, and 75% respectively. After fermentation with Aspergillus niger, the viscosity of CSL decreased by 27.8%, dry matters by 38.1%, which crude protein content increased by 5.6%. Although Aspergillus niger can decrease mycotoxins, its ability to enhance protein content is limited. We also found that several yeast strains can grow in CSL and utilize various small molecules compounds, including lactase. Among them, Cluivia romaces can decrease over 90% of lactase after fermentation. With Cluivia romaces, the crude protein content of CSL increased to 49%, 23.7% raise, showing higher protein potential enhancing ability than Aspergillus niger, and thus enhancing the value of CSL. To further explore the utilization value of CSL, we tested the Aspergillus niger mycelium producing from CSL fermentation. The mycelium yield reached 30 grams per liter with protein content of 46%, and its amino acid profile meets the standards of high quality protein. Therefore, the mycelium can be used as fungal protein. Food gel prepared by combining mycelia protein with soy protein isolated are similar to surimi patties, and their gel strength is close to that of fish cake, indicating potential as microbial alternative proteins. Our second case is the value-added treatment of wheat distillers dried solubles. The byproduct generated from ethanol products via fermentation of wheat flour by Saccharomyces cerevisiae is subjected to solid-liquid separation. The solid fraction is with DDG, and the liquid fraction is with DDS. With DDS has complex compositions consisting mainly about 18% crude protein and small molecules compounds such as lactic acid, xylose, and arabinose. After treated with cellulose, xylanize, pectinase, and proteinase, increase in the corresponding monomers is observed, which indicates that the solid components containing cellulose, hemicellulose, pectin, and protein. After degradation of corn DDS with proteinase, the highest amounts of glucose, xylose, and arabinose are released. Among these, the concentration of arabinose and xylose both exceeded 20 grams per liter, while the glucose concentration is nearly 10 grams per liter. Enzymatic degradation experiments indicate that the intercross linking of macromolecular compounds is a primary case of the high viscosity with DDS. After treated with different enzymes, macromolecular compounds are hydrolyzed into small molecular compounds, breaking the intercross linking state between macromolecules. As a result, the viscosity decreased by more than 50% in all cases, with the maximum reductions reaching 62%. Among these enzymes, xylanase exhibited the optimal performance in both treatment effects and economic cost. Therefore, it is recommended to use xylanase treatment to reduce the viscosity with DDS, thereby facilitating downstream processing. In order to further improve the property with DDS, we selected 3 yeast strains for fermentation, among which Gluiveromyces exhibited the best performance. It can efficiently use xylose and lactic acid, and all xylose was completely degraded after 48 hours of fermentation. Gluiveromyces can tolerate fermentation condition at 50 degrees, which further reduce the cost of microbial contamination and fermentation. After fermentation, the dry matter loss of wheat DDS is about 21%, while the crude protein content increases by a maximum of more than 80%. Additionally, wheat DDS become easier to dry after fermentation. We also assayed the protein content of these 3 yeast strains and found that all have a protein content exceeding 50%, demonstrating potential as microbial alternative proteins. In addition to value-added treatment of green byproducts, we also studied mycotoxins removal from green byproducts using enzymatic degradation strategies. Our approach is first explore microorganisms with mycotoxin degradation ability, then identify mycotoxins degrading enzymes from these microorganisms. We collected LV1 contaminated grain samples from over 20 high contamination area in China, isolated microorganisms that can grow in FB1, and finally identified 2 Bacillia strains. Then we identified an FB1 degradation enzymes from one of these strains. However, in particular applications, enzymes thermal stability or activity may be insufficient. Thus, we perform regional modification of these screened enzymes. For example, fusion with a short peptide sequence enhances the thermal stability of the hydrolyzed hydrolase. Subsequently, the modified ZN hydrolase was applied to various corn byproducts after optimization of degradation conditions. A degradation rate of ZN reached over 90% in just 1 hour for all tested materials. Besides exploring enzymes from microorganisms, we also mine mycotoxins degrading enzymes from known database and analyze their mechanisms of action. We mined lacase from the NCBI database and that can degrade multiple aflatoxins with a rate of 85% and analyzed the interaction sites between the enzyme and the aflatoxins via molecular docking. We then established a method for identifying aflatoxins degrading enzymes from genomes. First, sequencing microorganisms with the mycotoxins degrading functions, then predicting potential enzymes via molecular docking and verify their degradation ability. Finally, construct a database of all reported mycotoxins degrading enzymes to provide materials for the next round of identification. Finally, we constructed expression chassis cells for mycotoxins degrading enzymes. We expressed validated enzymes in yeast or E. coli and compared their activities under the same conditions, providing reliable enzymatical property indicators for subsequent practical applications. I welcome any questions or discussions. Thank you for your attention.
Okay, thank you. And we are going to our second talk from Argentina. The title is Sustainable Micro and Nanocomposite Materials Derived from Agroindustrial Byproducts and Their Application by Dr. María Alejandra García.
Good morning and good afternoon. I am María Alejandra García, Principal Researcher at CONICET, Associate Professor at the Faculty of Exact Science of the National University of La Plata, with a workplace at the Center for Research and Development in Food Science and Technology, CIDCA. First, I would like to thank the Chinese Academy of Engineering for this opportunity and Dr. Noemí Zaritzky for the invitation to participate in the webinar. I will be presenting the talk Sustainable and Micro and Nanocomposite Materials Derived from Agroindustrial Byproducts and Their Applications. The outline of this talk is the following: an overview of the research line on the topic, the presentation of some development on edible coatings and biodegradable film for food and agronomic applications, and finally, the concluding remark. A survey of sources like Science Direct revealed that the topic of sustainable materials application is experiencing significant growth due to its academic and economic relevance, especially considering global efforts to minimize the use of synthetic materials given their impact on pollution and its effect on climate change. Many efforts have been made to develop recyclable, biodegradable, and compostable materials, and the use of these materials in various areas is identified by the corresponding logos. Regarding global bioplastic production, as Dr. Bernal already mentioned, the packaging sectors, both rigid and flexible, stand out. As for market purpose, we can see in the graph that developments in the agricultural sector are still in their early stage and requires further progress. Therefore, in this talk, we will focus on the agricultural and food applications of various biodegradable materials and edible coatings. First, I would like to explain how the line of research we developed at SIDCA under the direction of Dr. Zaritzky came about and evolved. The research line began in 1993 with the start of my doctoral thesis, supervised by Dr. Noemí Zaritzky and co-supervised by Dr. Miriam Martino, to whom I am deeply grateful for the training I received. We began by developing edible coating for extending the shelf life of strawberries based on cornstarch. We studied the effect of adding glycerin and sorbitol as plasticizers, as well as the use of potassium sorbate as antimicrobial agent in the formulation. We developed and characterized films adapting specific methodologies for synthetic materials. In the case of the coating, we studied the quality attributes that determine the shelf life of the fruit. During my postdoctoral fellowship, we began studying coatings and films based on other hydrocolloids, such as cellulose derivative, chitosan, and keffiran. We decided to begin our research with edible coating, a challenge since the formulation development have to be adaptive to the requirement of the product being coated. In particular, we chose strawberry, a highly perishable fruit with a very short shelf life. We optimized the formulations and the application method for the coatings, which had to be imperceptible to ensure consumer acceptance. We verified the uniformity of the coating by iodine staining and achieved a shelf life of 21 days for the coated products, more than 7 days longer than the control. I've included some of the published work on this topic in case of interest. Along these lines, we developed edible coatings based on cellulose derivative for potatoes and dough subject to frying. The coating significantly reduced oil absorption during frying, as shown in the graph, and maintained their integrity. In a study led by Dr. Zaritzky, the frying process of dough with and without coating was a mathematical model, a process involving the simultaneous transfer of energy and mass. Since 2011, we have continued our research focus on the development of biodegradable films, studying matrices based on native starches such as corn, cassava, and aipa, as well as modified starches. We move from laboratory scale work to evaluating scaling alternatives such as extraction and thermocompression. We develop active materials that allow for the controlled release of antimicrobial for food or fertilizers for agronomic applications. We reinforce the matrices with reinforcing agents derived from the use of agroindustrial byproducts. We develop biodegradable foams, nanocomposite materials, bioadhesive, and smart materials for food applications. These developments are framed within the principles of the circular economy. Next, I will present some progress on these topics. As part of Dr. Florencia Versino's doctoral thesis, we studied the use of cassava starch extraction byproducts, specifically the bagasse and remaining spills, as reinforcement for cassava starch-based films. We characterized the byproducts by studying their morphology and particle size distribution using scanning electron microscopy. We also determined their chemical composition, observing that the peel residue is a source of lignocellulosic fibers, while the bagasse contains starch granules remaining from the extraction process, as seen under same observations. Both bagasse and peel residue were used as reinforcement for starch-based films obtained by thermocompression. This work was carried out in collaboration with Dr. Olivia Lopez. While the reinforcement did not modify significantly the water vapor permeability of the materials, a clear effect was observed on the mechanical properties, where both acted as a reinforcement, increasing both the elastic modulus and the material strength. Furthermore, while the byproducts, particularly the peel residue, impart color to the material, as you can see in the photograph, they also improve this UV barrier capacity, which is a very interesting property for its use in agronomic application, such as soil mulching. The scaling up of biodegradable materials based on native or modified starch, specifically acetylated starch, was also explored using extrusion and blow molding, demonstrating that it is possible to use the equipment for obtaining synthetic material for this purpose. This study was carried out through a collaborative project with the University of Londrina in Brazil. Regarding the development of material for agronomic application, the methods of obtaining them must be considered first. While the most widely used technique at laboratory scale is the casting one, to scale up the process, tape casting can be used as a semi-industrial scale. As we mentioned previously, extrusion is a very advantageous technique because it allows the use of equipment commonly used to obtain synthetic counterparts. When evaluating the most relevant properties regarding this application, we must highlight the optical ones, since in soil mulching applications, both UV barrier capacity and PAR transmissivity are important. PAR transmissivity corresponds to the spectral region that favors photosynthesis in the case of the crop's width. It's also to know its gas and water vapor barrier properties and its heat sealing capacity for applications such as tunnel crops or silo bags. And of course, these materials are expected to be biodegradable. And at the end, their disintegration in soil is evaluated, since in the case of mulching, this allows not only minimizing pollution, but also reducing the costs associated with post-harvest plastic collection operations. In this case, cassava starch-based film reinforced with bagasse were used as soil mulch under real field conditions. As you can see in the photographs, these materials began to degrade after 21 days to expose to air. During these times, a decrease in PAR transmissivity was also observed. When their biodegradation in soil was evaluated, 42 days were required for complete disintegrations. These materials could be easily obtained using the tape casting technique and would be suitable for short-cycle crops. These materials were functionalized with urea, allowing the controlled release of fertilizer within a time frame compatible with growth cycles of tomato seedling. These active films were used in application for tomato cultivation, both for developing pot for seedling and for supplementing the pot containing the seedling. It was observed that the pot with the dispensers allow for better plant development, as you can see in figure F. Here, figure F. With a greater nitrogen fixation in the roots and leaves, and a large leaf area. This indicates that this plant had better development, resulting in increased crop productivity. I would now like to present some progress related to the development of biodegradable materials for food applications. First, I will discuss the work we carry out as part of Dr. Julieta Boff's doctoral thesis at the National University of Entre Rios and her research fellowship at the Polytechnic University of Valencia in Spain. We developed films based on starch and chitosan, optimize the formulation and functionalize them by adding active compounds derived from citrus industry byproducts such as lemon essential oil and grapefruit sweet extract, both of which have antimicrobial properties. Among the desirable properties of food packaging materials are mechanical resistance, UV barrier capacity, heat sealing capability, and the ability to create a selective barrier to gas exchange between the product and the atmosphere through the material. The developed films were used to create heat sealable biodegradable bags for packaging blueberries. This product was chosen because Argentina is one of the world's largest blueberry producers, exporting 80% of its productions. The packagings require special characteristics to withstand the condition of maritime transport. Traditionally, PET clam shells were used for this purpose. A trial was conducted simulating the conditions of maritime transport in containers and subsequent commercialization, also considering thermal abuse. The packaging obtained with the composite and active films reduced the incidence of rot with a weight loss of less than 3%, thus minimizing economic losses during transport. Furthermore, the fruit maintained its antioxidant capacity and phenolic compound content, which are highly valued in this type of minimally processed products. In this case, films were developed using chitosan dissolved in propionic acid, a preservative used in dough discs known in Argentina as empanadas, a mass consumption product. These films were used as separators between the pastry dough discs, and their effectiveness in extending the shelf life of preservative-free dough compared to their synthetic counterpart was demonstrated. This work was selected for the 2012 Innovar Awards and was carried out in collaboration with Dr. Rivero, Pinotti, and Januzzi. As part of Dr. Florencia Ortega's doctoral thesis, silver nanoparticles were synthesized using green techniques in the film-forming suspension of cornstarch-based films. Natural reducing agents derived from lemon juice were used, and the nanoparticles were also obtained by laser ablation. Nanocomposite materials were developed and characterized for their relevant properties. The nanometric size of the nanoparticles and the antimicrobial capacity of the nanocomposite films were confirmed. Through heat sealing, bags were obtained and used for packaging fresh cheese, demonstrating their effectiveness in extending the product's shelf life by 7 days under refrigerated conditions. However, in the case of nanocomposite material in contact with food, further tests are necessary to study their safety. For this purpose, migration tests of silver nanoparticles into food simulants were performed, demonstrated in all cases that the migration was below the global migration limit permitted by international regulations. The cytotoxicity of the materials was also studied on 2 model cell lines, Caco cells and Vero cells. It was observed that in the case of nanoparticles obtained by laser ablation, cell viability is lower and therefore could be potentially cytotoxic. Biodegradation in soil was evaluated, which was not affected by the presence of the nanoparticles. In this case, it is necessary to evaluate ecotoxicity of the remaining compost, showing positive results in this regard. On the other hand, as part of Dr. Juliana Monroy's doctoral thesis, we developed bioadhesive based on cassava starch chemically modified with polycarboxylic acid, such as citric acid and BTCA, as well as sodium hydroxide and urea. Optimizing the formulation allows us to control the rheological behavior and adhesion of the bioadhesive on different substrates. Since they were designed for its use in packaging area, we studied the bond strength and resistance between substrates such as paper and glass, considering their use for label applications. In this case, we also evaluate the easiness of label removal, taking into account bottle recycling. We also assess the bonding of paper to paper and cardboard to cardboard, considering the assembly of different types of packagings. Furthermore, by reusing gelatin from pharmaceutical industry waste, we generated during the preparation of drug capsule, we developed a double-sided tape that exhibits excellent resistance and allowing it to be used on masonry walls such as doorlock. Sustainable panels were obtained through thermocompression using formulated adhesive and byproducts from wood processing and other agro-industrial byproducts, such as the powder remaining from yerba mate production. These materials could be used in the design of trays for packaging and marketing of various products. The mechanical properties of the panels were characterized through 3-point bending tests, and their tribological behavior was evaluated to study their wear. During Dr. Versino's postdoctoral fellowship, in collaboration with Dr. Olivia Lopez, we developed starch-based expanded materials reinforced with a byproduct of the oil industry, specifically the sunflower press residue. This material offers a sustainable alternative to expanded polystyrene for dry manufacturing. The goal of this material is to achieve an aggregated structure by incorporating a expanding agent into the formulation. While the addition of the filler improves mechanical strength, its content is limited by the increased material density and the potential for structural collapse. Finally, we are working on the comprehensive use of an undervalued crop, the Jerusalem artichoke, a plant from the Asteraceae family related to the sunflower, which has tubers that accumulate inulin as reserve. In the thesis of Dana Vega, in collaboration with Dr. Sonia Viña, we processed these tubers to obtain flour and use it as an ingredient in the formulation of functional foods, since the inulin and the fructooligosaccharides present in the flour are prebiotic and therefore help to improve the consumer's health. The aerial part of the plant remains after the processing of the tubers and can be used as forage. However, in Luisa Sierra Montes' doctoral thesis, we valorize the residue and use it to obtain a biodegradable films of thermoplastic starch and PBAT. This demonstrated the effective of the lignocellulosic fiber reinforcement on the material's mechanical properties without compromising its biodegradation in soil, indicating that this material could be useful for agronomic application. This is a clear example of how our research are aligned with the principles of the circular economy. Thus, We can conclude that from different industrial byproducts, it is possible to recover not only biopolymers, but also functional compounds, which can be used as matrices, forming, reinforcing agent, and active compounds of biodegradable materials. These materials have proven to be effective in various agricultural and food applications. I would like to highlight that since 2018, our country, Argentina, has been implementing the Argentine Byproduct Seal, which highlights, promotes, and values the use of byproducts of national origin. This seal has been promoted by government agencies. In the photograph, you can see some of the products that have received the seal, from a bicycle with bamboo parts to cutlery, cosmetic lines, and party suppliers. I would like to introduce and thank the research team that participate in the development I mentioned, and I also thank the organization that funded the project and made all this research possible. Thank you for your attention.
Okay, thank you, Dr. Garcia. And we are continuing with the third presentation from China, building sustainable food system in China, and is given by Dr. Rui Liu.
Good morning, ladies and gentlemen. We're glad to attend this meeting. My name is Liu Rui from the Institute of Food and Nutrition Development, Ministry of Agriculture and Rural Affairs, China. I also work for China Green Food Association. Today's report name is Building Sustainable Food Systems in China. Firstly, we need to discuss a new concept, retro food. This concept was proposed by Chinese leader Xi Jinping. It's a new perspective on food. We need to shift the traditional perspective of grain security to a concept of food security. Food security refers to that people have access to sufficient, hygienic, nutritious, and diverse food. It also demands that food production, circulation, and consumption pay attention to resource and environmental protection, achieving green and sustainable development. Green security and food security have different evaluation indicators. From these indicators, we can find the differences in them. Green security pays attention to grain planting area, production quantity, per capita variability, inventory levels, dependence on import, grain price, fluctuations, and so on. But for food security, we must pay attention to multi-level content, include supply security, quality assurance, nutritional security, resource security, and sustainable development. The first level is supply security. Supply security includes the area of cultivation and livestock farming, food production efficiency, total output, and per capita availability of grains, oils, vegetables, fruits, meat, eggs, and milk. Self-sufficiency rates of major agricultural products, such as grains and pork, inventory levels of major agricultural products, and the price fluctuations of major agricultural products. The second level is quality assurance. It includes the pass rate of agricultural product quality and safety, the supply level of green and high-quality agricultural products, as well as the monitoring, evaluation, and the regulatory capabilities for agricultural product quality and safety risks. The third level is nutritional security. It includes per capita food energy supply, per capita food protein supply, proportion of grain food supply, prevalence of malnutrition among residents, anemia rate among residents, and the starting rate among children under 5 years old. The fourth level is resource security. It includes arable land resources, water, grassland, forest, marine precious resources. The highest level is sustainable development. It includes ratio of agricultural capital input to output, level of food loss and waste, level of waste recycling and utilization, carbon emissions, water usage, biodiversity level, contribution rate of technological progress, resident scientific literacy, and so on. Regarding building the sustainable food system, what have we done? The first work to develop green agriculture and green food. Green agriculture is a better combination of organic agriculture and modern agricultural technology. It advocates protecting the excellent ecological environment as the foundation, producing safe and high-quality products as the core, adhering to the rational development and utilization of resources, and harmonizing the relationship between humans and nature. Currently, it mainly promotes measures such as saving land, water, seeds, and energy, reducing pesticides and fertilizers, and recycling resources. These figures are the Green Food Certification logo and the Green Food Production Materials Certification logo. Second one is to develop nutrition-sensitive agriculture. In 2014, the second International Conference on Nutrition, jointly organized by the FAO and WHO. Overnutrition and hidden hunger became key areas of focus. In the meeting, FAO systematically explained the concept of nutrition-sensitive agriculture, proposing that nutrition-sensitive agriculture is an agricultural development approach focused on the nutrition of food, emphasizing nutrient-rich foods, dietary diversity, and food fortification as a core to eliminating malnutrition and micronutrient deficiencies. In 2017, FAO proposed nutrition-sensitive agriculture is a new agricultural approach that aims to meet the dietary needs of the population in a sustainable way and ensuring the production of various foods that are sufficient in quantity, high in quality, reasonably priced, nutritious, culturally appropriate, and safe, and nutrition and health as the ultimate goals and measures. We translate some book from FAO, for example, the nutrition sensitive agriculture and food systems in practice. We also develop some policy document. In these documents, we propose that nutrition guides the consumption guides the production. We also do some research on nutrition-oriented technology and standards. We develop some high nutrient density varieties. For example, the zinc biofortified wheat, zinc biofortified wheat, high folate corn. We also use some cultivation and breeding regulation technology to produce some high-quality functional agricultural products. For example, the flaxseed pork. We use the flaxseed to feed the pig. So the content of unsaturated fat acids in this pork is very high. It's very healthy. We also develop some nutritional standards in China. We pay attention to the popularization of food nutrition knowledge and the guidance on reasons food consumption. Include the food nutrition education, guiding consumer choices through the labels and signaling, improving the food environment through establishing nutritious restaurants and cafeterias. We also establish a sound, nutrition-oriented, sustainable food policy system. We develop the nutrition economic discipline and to promote a good food nutrition industry environment through the advertising and make some agricultural green development policy, including the carbon footprint and the green finance. This figure shows the nutritional standard in China. And this table is the Chengdu Community Nutritious Class and the University Nutrition Smart Cafeteria Segment. We jointly establish product certifications on levels such as food grade certification, plant-based food certification, low GI food certification, and health food certification, and so on. We can see the ecological food certification. China products of eco-origin approved certification and organic food certification, and so on. We gain some experience from this work. First, rethinking the relationship between agriculture, nutrition, and health from a system perspective. Second, analyzing the problems in agriculture and food systems from the concept of sustainable development. Third, rebuilding the agricultural industry chain and food nutrition value chain with a nutrition-oriented approach. Third work is to develop plant-based food. The World Economic Forum has proposed 3 possible ways to sustainably and healthily meet the world's growing demand for protein. Last, way is to find better alternative protein sources. We know that the food production accounts for about a quarter of global greenhouse gas emissions. Of them, the production of animal-based foods accounts for 60% of greenhouse gas emissions in agricultural production. So we want to develop more plant-based foods. This table shows the plant-based meat production technology and its advantages and disadvantages. The technology includes squeezing method, spinning, and shear method. The twin screw wet extrusion is the most common method to produce plant-based meat. This table shows the basic plant-based meat formula. For example, the plant-based protein includes soybean protein, pea protein, and wheat protein to supply the texture, and the nutritional content of the plant-based meat. We also use the meat flavor essences, ester extract, to enhance the flavor. We use the fat. Plant fat includes corn oil, coconut oil, and adhesive substance and some plant pigment. We released a report with Xinhua Met named Plant-Based Meat Carbon Reduction Insights Report. In this report, we compared the carbon emission of different types of plant-based meat and animal-based meat. In this figure, for example, this one. We compared the carbon emission equivalent per kilogram of beef is 46.2 kilogram. But for the plant-based beef, only 1.0. It can reduce carbon emission by 97.7%. The reduced quantity is equivalent to the carbon emissions from a medium-sized goods line vehicle traveling over 200 kilometers. And we also developed some plant-based milk. Plant milk is a plant-based protein beverage made from the legumes, nuts, grains, and other seeds, and has an appearance and taste similar to dairy products. Plant-based milk can alleviate the environmental and animal welfare issues compared with the traditional dairy products. The types of the plant-based beverage. For example, the soybean milk, peas milk, rice milk, oat milk. These milk are very popular milk. This table shows the environmental impact of producing 1 liter of milk. We can see from this table, compared to the producing milk, producing oat milk requires much less carbon emissions, water consumptions, and land usage. Sales of plant-based protein drinks in China have increased by 1,000%, with the revenue growing by 1,800%. According to a research report from the Foco Nutrition and Health Research Institute, the market size for plant-based protein beverages in China has reached 50 billion yuan and is growing rapidly at an annual rate of 20%. This table shows the classification of some plant-based milk companies and their products in China. In 2021, the first white paper on China's oat milk industry was released. I'm the chief author of this white paper. Oat milk received significant attention, but the main discussions in the industry still focus on exploratory topics such as definitions, raw materials, domestic and international market tracking, and how China can emulate and surpass others. But after 2 years of rapid development, plant-based milk has gradually become an independent category, no longer existing merely as a substitute for dairy products. We released another white paper, the 2023 China Oat Milk Industry White Paper. This book provides a systematic summary of the industry's development of production innovation and explores the 8 new elements of the new plant-based 2.0 era. In the second white paper, 8 new developments in the developments of oat was released. New definition, new standard, new ingredients, new process, points of nutrition, new consumption, dictionaries, new social value, and new trends. The fourth work is to develop carbon labeling. Carbon footprint labeling refers to informing consumers of greenhouse gas emissions through labels by calculating and analyzing the carbon emissions throughout the product's entire life cycle, aiming to mitigate global warming and reduce carbon emissions, thereby influencing the consumer's purchasing behavior. We formulated a group standards in 2023. This is the carbon label of the products produced by the Chinese factory of my partner Oatly. The carbon footprint of 1 liter of oat milk is only 0.6 kilograms of carbon dioxide equivalent. Oat milk has a 68% lower impact on the climate compared to the animal milk. 5 other works include the reduced losses across the entire industry chain, promote local production and local consumption to shorten food miles, reduce distribution links and reform product and sales models, and develop the ready-to-eat and pre-prepared vegetable industry. Exploring unique food resources to develop some food and medicine, to use resources, to use the microbial resources, to develop the forage and the sandy area resources, and build the marine ranches and develop deep sea aquaculture, to develop urban facility agriculture, to develop cell agriculture. For example, the cell cultured meat and fermented proteins. We also emphasize the food education, improving the scientific literacy of the entire population. We make a lot of some policy document. For example, the Chinese dietary guidelines, outline of food and nutrition development in China, and the national nutrition plans. These documents released by the Chinese government to promote the conception of healthy eating and enhance awareness of food and nutrition. The conclusion: the future people desire for a better life and upgraded consumption poses higher demands on food supply. Achieving a good perspective on food requires collaboration from multiple parties and various approaches to ensure national food security, nutritional security, and ecological security, while promoting a food system that is more efficient, inclusive, stable, and sustainable. That's all. Thank you for your listening.
Okay, thank you very much. We are continuing our webinar with the third presentation from Argentina. The title is Food Waste Valorization for the Remediation of Contaminated Water, and is given by Noemí Zaritzky.
My name is Dr. Noemí Zaritzky, and the title of this presentation is Food Waste Valorization for the Remediation of Contaminated Water. I work in the Chemical Engineering Department, Faculty of Engineering, at the National University of La Plata, Argentina. Also at the Center of Research and Development in Food Science and Technology. Our research group has worked on the development of processing technologies for the use of new species of crabs from the Argentine Patagonia in the food industry. Heat transfer during thermal treatment, pasteurization, and freezing were addressed and mathematically modeled. Residual exoskeletons of crabs were accumulated in the process. In the processing of crustaceans for the use of the edible muscles, solid waste, or exoskeletons, that are difficult to dispose of are generated, and they accumulate in landfills, constituting an environmental pollutant. For example, in the industrialization of shrimp meat, the exoskeleton represents between 35 to 50% of its total weight. The residual exoskeleton from crustaceans contain chitin, which is a natural, abundant, and non-toxic material. Chitin is a source of chitosan, a high-value biopolymer that can be used for water remediation. Valorizing food waste for water remediation involves converting it into material that are applied to remove pollutants from contaminated water. This process is a key part of the circular economy, turning a waste problem into an environmental solution. Extraction of chitin from waste involves acid demineralization, alkali deproteinization, and decoloration. We work on the optimization of the extraction methods of chitin and the deacetylation procedure under alkaline conditions to obtain chitosan. The yield in this last step was 76%. Chitosan is a polyaminosaccharide cationic polyelectrolyte containing amino groups. It is biodegradable and biocompatible, having numerous applications in the pharmaceutical, cosmetic, food, biomedical, chemical, and textile industry. Chitosan has three types of reactive functional groups: amino groups and hydroxyl groups. The acetylation degree and molecular weight are important properties to characterize this biopolymer. The acetylation degree is the proportion of glucosamine units relative to the total number of glucosamine and N-acetylglucosamine units. It was determined by infrared spectroscopy Fourier transform, following characteristic bands of N-acetyl groups and amino groups. The average viscometric molecular weight was obtained from the intrinsic viscosity. We work with diluted polymeric solution having rheological Newtonian behavior and measure the relative viscosity, that is, the viscosity of the diluted polymeric solution divided by the viscosity of the pure solvent. From this value, we calculated the specific, reduced, and inherent viscosity. Intrinsic viscosity was determined by extrapolating the values of reduced or inherent viscosity at polymer concentrations tending to zero, and the intrinsic viscosity was determined by Huygens equation and Kramer equation. Intrinsic viscosity is a measure of the hydrodynamic volume occupied by macromolecules in solution. The viscometric average molecular weight was determined according to the Markhovin-Kuhn-Sakurada equation, where K and A are coefficients obtained by Rinaudo and that depend on the solvent polymer system. Chitosan is commercialized as a low, medium, and high molecular weight compound with average values of 120 to 600 kilodalton. In this work that we published, chitosan biopolymer was used in coagulation and flocculation processes for the clarification of emulsified oily wastewater. Significant part of oil is normally present in the emulsified form that is difficult to separate from the water phase, and it is an important challenge in petroleum and petrochemical industry. The presence of emulsified oils in wastewater causes significant environmental problems. At the left, we can see the original oil-water emulsion and the micrographs of the emulsions by light microscopy. We calculate the average diameter of the droplets, D for 3, and we use several techniques such as the removal of chemical oxygen demand, the relative turbidity, the relative length of the clarified zone, and measurements of zeta potential. Oil-water emulsions were formulated with crude oil, petroleum from the Argentine Patagonia, water, and sodium dodecyl sulfate, that is an anionic surfactant. We can see that the addition of chitosan, that is a cationic polyelectrolyte, produced the destabilization of the emulsion by charge neutralization. At the right, we can see the decrease of residual turbidity in the emulsion with and without sodium dodecyl sulfate after the addition of an adequate dose of chitosan. A response surface methodology and central composite design were applied to optimize the influence of chitosan and sodium dodecyl sulfate, the surfactant, on the performance of the demulsification process. A desirability test allowed to calculate the optimal doses of chitosan to produce minimum values of residual turbidity and zeta potential and maximum values of clarified zone and chemical oxygen demand removal. We developed a practical and predictive method based on the optimized results that allows the application of adequate doses of chitosan and the surfactant to demulsificate and clarify crude oil water emulsion in a wide range of concentrations. Kinetics of emulsion destabilization was measured with a TurbiScan vertical scanning analyzer based on multiple light scattering by recording the backscattering profiles that show the increase of the clarified zone with time. A kinetic model based on first-order equations for both stage coagulation, flocculation, and settling of the flux was proposed to describe clarification. Coagulation flocculation was produced in less than 3 hours. The proposed model is a useful tool for predicting clarification times. In conclusion, chitosan is a potent flocculating coagulating agent in wastewater emulsified system from petroleum industry. Adsorption-based methods are promising for the removal of water contaminants because they can be used in small-scale treatment plants, they are easy to operate, and can have a high regenerative capacity. Adsorption using biopolymers is a recommended process due to the economical and technical advantages. Chitosan biopolymer was used in adsorption processes for the removal of hexavalent chromium, arsenic, and fluoride from groundwater and azoic colorants. In the batch adsorption experiments, the percentage of contaminant removal under different tested conditions was evaluated. We also measured the adsorption capacity at equilibrium conditions, that is the amount of contaminant adsorbed per unit weight of adsorbent at equilibrium. These are the adsorption kinetic models that we tested with the respective equations: pseudo first order, pseudo second order, Elovich interparticle diffusion, and mixed surface reaction and diffusion control kinetic model. The tested adsorption isotherm equations were Langmuir, Freundlich, Temkin, Redlich-Peterson, and Dubinin-Raduckevich. From the adsorption experiments at different temperatures, we determined the thermodynamic parameters of the adsorption process. We applied Van Hoff equation to calculate enthalpy and entropy from the equilibrium distribution contact, and also we calculate the Gibbs free energy. Negative values of delta G indicate that the adsorption is spontaneous and feasible. Water contamination with hexavalent chromium, chromate and dichromate is a critical problem because they tend to persist and accumulate in the environment. Hexavalent chromium is one of the most toxic contaminants and is released in the environment due to different anthropogenic activities: textile, electroplating, leather tanning, cement preservation paints, pigments, and metallurgy industry. The maximum contaminant level for hexavalent chromium into inland surface waters is 0.1 milligrams per liter. In this work, we synthesized reticulated chitosan micro and nanoparticles by ionic cross-linking of chitosan using a non-toxic reagent, tripolyphosphate. Tripolyphosphate is a polyanion that interacts with the protonated amino groups of chitosan, forming the cross-linked network that is shown in the figure, and generating micro and nanoparticles in adequate concentration. Articulated micro nanoparticles of chitosan with an average diameter on 100 nanometer were synthesized by ionic gelation of chitosan with tripolyphosphate and characterized by scanning electron microscopy, size distribution, and zeta potential. The highest values of zeta potential were achieved at low pH. Hexavalent chromium exists at negatively charged ions chromate and dichromate. This is in contrast to trivalent chromium, which is a cation. Removal of hexavalent chromium by chitosan and chitosan nanoparticles were tested at different initial chromium concentration, doses, contact time, and pH values. Chromium concentrations were determined by flame atomic absorption spectroscopy. Maximum hexavalent chromium absorption on chitosan unmodified particles occurred at pH of 4. In this case, the functional groups become protonated, resulting in a stronger attraction for the negatively charged hexavalent chromium. In the case of cross-linked nanoparticles, the highest removal performance was achieved at pH of 2. Under this condition, unmodified chitosan is an unstable matrix. As can be observed in the figure, equilibrium adsorption isotherm for chitosan and chitosan nanoparticles was satisfactorily described by Langmuir equation, where Qm is the maximum adsorption capacity and Kl is the Langmuir constant. Pseudo second-order kinetics fitted the experimental data well. It means the overall adsorption reaction rate is controlled by a chemical reaction or chemisorption. That is, the rate-limiting step is the binding sharing of electrons. Interactions between the micronanoparticles and the adsorbed chromium were analyzed by Fourier transform infrared spectroscopy. Hexavalent chromium is 500 times more toxic, mutagenic, and carcinogenic than trivalent chromium, that is stable and non-toxic. The oxidation state of the adsorbed chromium was determined by chemical analysis and by X-ray absorption near-edge structure spectroscopy in a Rigaku equipment. In the case of unmodified chitosan particles, hexavalent chromium was adsorbed without further modification. In contrast, when adsorption was performed on reticulated nanoparticles, more than 60% of the adsorbed chromium was reduced to trivalent chromium. This is a very important result because chitosan nanoparticles can be considered an efficient removal and detoxification technique. They act not only as adsorbent, but also as electron donors for hexavalent chromium reduction to trivalent chromium on the surface of the particles. Chitosan was also used for arsenic removal. Arsenic is considered one of the most serious inorganic contaminants in groundwater. The maximum limit is 0.01 milligrams per liter. Many countries across the world have reported moderate to high concentration of arsenic in groundwater. The problem is mainly caused by natural geological formation. The chronic exposure to arsenic leads to arsenic poisoning or arsenicosis. Exposure to high concentrations in drinking water is associated with an increased risk of lung, skin, and bladder cancers, skin lesions, cardiovascular, neurological, and respiratory disease. In this work, we synthesized functional iron chitosan microspheres by ionotropic gelation of chitosan and ferric nitrate for the removal of arsenic from water. We used different iron concentrations in the particles and scanning electron microscopy coupled to an energy dispersive X-ray detector was used for the microanalysis of the spheres. Atomic absorption spectrometer was used to measure arsenic concentration in water. Iron chitosan particles were effective for arsenic absorption in a wide range of pH, with removals higher than 90%. Kinetic data of arsenic absorption under all tested initial concentrations fitted well with the pseudo second-order kinetic model. We analyzed the FTIR spectra of the tested microsphere pre- and post-arsenic absorption. Sorption isotherm experimental data were satisfactorily fitted with the Langmuir equation. The synthesized chitosan iron microspheres show a very good arsenic absorption capacity. The material can be reused after 4 successive adsorption cycles, and interferic anions such as nitrate, carbonate, and phosphate do not affect their performance. In relation to fluoride contamination in groundwater, it has been reported as a serious problem around the world. Fluoride contamination in aquifers can be caused by natural geological processes and by anthropogenic activities. The consumption of groundwater with fluoride ions can cause several health problems: dental and skeletal fluorosis, osteoporosis, infertility, and arthritis. When groundwater contains concentrations higher than 10 ppm, it can accelerate diseases such as hypertension, cancer, and neurological problems. The permissible limit of fluoride in drinking water ranges between 1 and 1.5 ppm. In this work, we synthesized functional calcium phosphate chitosan adsorbents for fluoride removal from water with different proportion of calcium by ionotropic gelation and by freeze-gelled matrices. Adsorbents were analyzed by scanning electron microscopy and FTIR. Fluoride concentration was analyzed using a colorimetric method that involved the reaction of fluoride with a red zirconium dye solution. We can observe in the figure the structure of the particles analyzed by scanning electron microscopy and the EDX analysis. Calcium phosphate chitosan adsorbent synthesized by ionotropic gelation and containing 0.7% of calcium was the best option for fluoride removal. Pseudo second order gave the most satisfactory fit for fluoride removal kinetics. On the other side, Langmuir equation was the model that best fitted experimental data of equilibrium sorption isotherm. The particles were analyzed by infrared spectroscopy and X-ray diffractograms. XPS, X-ray photoelectron spectroscopy, was also used to characterize the particles. It is a surface-sensitive technique. The red points in the scanning electron microscopy surface mapping correspond to the adsorbent fluoride. The removal efficiency was slightly reduced in the presence of nitrate, carbonate, and arsenate. In conclusion, the calcium phosphate chitosan adsorbents constitute a suitable and emerging material for water defluorination. The contamination of water due to the presence of synthetic dyes is a serious environmental problem. The chemical structure of the dyes is important because they can break down to form hazardous chemical substances, For example, azo dyes can form aromatic amines, which are human carcinogenic. We analyze the performance of chitosan-based materials to remove a reactive azo colorant. In this work, chitosan particles were synthesized by coacervation precipitation technique in alkali medium, and they were used as biosorbent material to remove the azo dye. We can see the stereomicroscope micrographs and the scanning electron microscopy surface morphology. The particles show high removal percentage and absorption capacity. The maximum performance was at pH of 4. We can observe the FTIR spectra of the coacervated particles before and after the adsorption process. Also, the adsorption isotherms that were obtained at different temperatures. Redlich-Peterson equation fit the experimental values satisfactorily. Thermodynamic parameters were evaluated in all cases. The mixed surface reaction and diffusion control kinetic model fit the results of adsorption kinetics satisfactorily. Desorption and regeneration experiments show that the particles can be used in adsorption-desorption cycles. We also synthesized cross-linked oxalic acid chitosan hydrogels that were characterized and tested for the adsorption of azo dyes. Oxalic acid was selected because it is a natural organic acid, an eco-friendly cross-linking agent that reduces swelling and improves chemical stability of the chitosan particles at low pH. Adsorption performance in batch size show a maximum percentage of removal of 90% at pH 4. Ionic cross-linking of chitosan with oxalic acid enhance the adsorption capacity with better structural and functional properties. In this work, a biocomposite adsorbent was synthesized using 75% alumina ceramic particles coated with chitosan cross-linking with oxalic acid. They were used for the removal of the azo dye from wastewater. The physicochemical and structural characteristics of the matrix were evaluated by Z potential, FTIR, scanning electron microscopy, X-ray diffraction, and porosity. Biocomposites show high performance at low pH. Langmuir sorption isotherm and pseudo second-order kinetics provided the best fit. The electrostatic interaction between the azo dye due to the sulfonate groups and the free amino groups of chitosan enable successive desorption regeneration cycles. Experiments performed at different temperatures allow the calculation of the thermodynamic parameters, showing that the adsorption process was spontaneous, exothermic, and enthalpy controlled. Finally, the removal of the azo colorant was studied in fixed bed columns filled with the ceramic particles coated with cross-linked chitosan oxalic acid. The dynamic adsorption performance was analyzed from the experimental breakthrough curves at different operated conditions: bed depth, volumetric flow rate, and dye inlet concentration. The breakthrough curves were obtained by plotting dimensionless concentration as a function of time. Different dynamic adsorption models were applied to fit experimental data. Bohart Adams, Thomas, and June Nelson. The best models that fit the experimental breakthrough curves were Logistic and Jan. These equations enable the scaling up of the industrial process under dynamic conditions. In conclusion, the present work proposed a novel biosorbent material contributing to the analysis of industrial dye removal in continuous fixed bed columns. This is the list of our publications. In conclusion, valorization of food waste presents a cost-effective, eco-friendly strategy for circular waste management. Food waste-based water remediation supports global pollution control and environment sustainability. Thank you for your attention.
Okay. We are now present the last talk that is given by Liu Chang, and the title is From Byproduct to Golden Feed, Secondary Value Creation for Green Resources.
Good morning and good evening. Here's Yun from Builder Group. It's my pleasure to participate in today's webinar on behalf of Builder. My presentation's topic is From Byproduct to Golden Feed, the secondary value creation for the green resources. As the food expert, I believe all of us are aware of the following challenges. In order to feed 7.8 billion people on the world, 25% global GHG emission is from agriculture, 70% of the total fresh water usage for agriculture. 1/3 of global energy goes into food production, while 1/3 of all food product is lost or wasted. And 20% of deaths worldwide are attributed to the poor diet. The more worse is estimated by 2050, there are more people, around 10 billion, and less arable land, 35 less agricultural land. How to tackle this huge challenge? As a company, Builder is a marketing leader in many areas, especially for food and green processing. So we believe we can contribute to tackle these challenges. For example, for many solutions, worldwide, 65% flour are manufactured by Builder equipment and solutions. So we believe we can help our customers, food manufacturers or green processors, to reduce the energy consumption, waste, and water usage. In China, the government also pay a lot of attention to the food security and also encourage what we call the dual carbon strategy. That means by 2030, the carbon emission reach the peak, and 2060 will be neutralization of carbon footprint. And CODC, CDRC, and the State Council also have regulations encourage a circular economy and food against food waste regulations to tackle these challenges, and also encourage the innovative solutions to solve these challenges. If we zoom in the food processing industries, annually in China, we have over 180 million tons byproduct from the grain processing. how to better use this byproduct by upcycling them, I think we see huge potential. Because current byproduct treatment waste is caused resource waste, economic losses, environment pressures, and food safety concerns. By the innovative ways, builders convert from the byproduct to golden feed. You can see several different recovery paths to convert this byproduct to standard feed, fermented feed, or high protein feed. That's several upcycling solutions provided by builder. But due to the time limits, I will focus two of them. One is a fermentation feed, the other is insect farming during today's webinar. Let's look at the fermented feed. In China, there are huge demand for the fermented feed. You can see the swan feed, poultry feed, aqua, ruminated feed totally established. The annually feed demand is around 280 million tons. That's huge. On the other side, from the spent grains, there are still very valuable nutrients or ingredients inside. When we look at the starch, protein, or other fat, fibers, it's lots of valuable nutrients inside. So we utilize the technologies to convert this spent grain to biofermented feed, enable large-scale standardized processing, achieving harmless and resourceful utilization of spent grains. This treatment method not only enhanced animal productivity and immunity, but also reduced the use of the antibiotics and other drugs, realizing the goal of reduce or even zero antibiotic use, thereby promoting a perfect economic the cycle of the agriculture, brewing, and livestock. Then to agriculture, it's a perfect loop to realize circular economy. Here is the build a standard process for fermented feed. It includes pre-drying, mixing, solid state fermentation, low temperature drying, sifting and grinding, blending, and packaging. So they can use spent grain or soybean meal as raw materials. They can also use other auxiliary materials like corn beans or bran, and the end product will be fermented feed. This fermented feed is a high-value protein expansion, and this reinforced the competitiveness of the feed players if they use fermented feed, because this from the fermented feeds have lower anti-nutritional factors and boost the digestibility and can help the feed player creating a differentiation brand and defensible technical mode. Builder can provide different solid-state fermentation chambers, depends on which production demand you need and different architecture layout and maybe different fermentation method. All these fermentation chambers are highly automated and digitalized, and with a fully adjustable and controllable production process. Here is some pictures for different fermented chambers available with builder solutions. For sure, these solid state fermentation chambers can also be used for other applications like soy sauce or koji production or bio brewing purpose. The second application of upcycler examples is insect farming. Actually, I should call it insect factory. The insect can be better address the challenges because we mentioned for coal or grain processing worldwide is 7 or 8 million tons of this byproduct. But during the food processing, retail and consumer, they are more worldwide. It's around 1.3 billion tons of organic residues. And by using insect plant or insect factory, around 70% protein can be recovered. Here is the processing map. We can use the organic residue as a feedstock for the larvae of a black soldier fly, and using the rearing process, we can grow the larvae from 10 microgram to around 200 microgram. Then we do the processing, convert this larvae to valuable nutrition like lipids or protein meal, and even the residue can be fertilizer for plant nutrition. So for the protein meal, it have balanced amino acid profile and good digestibility for the animals. And this insect lipid is very easy digestible energy, with also have high uric acid content. And this fertilizer can have slow nutrition release over time, and with cheating as a functional component. Here is the layout of a insect plant with around 20,000 square meters. We can treat upcycling 100 tons raw material per year. And here is the cycle from agriculture to the brewing, to the insect, to the animal nutrition feed, and also the fertilizer for the sorghum. And then sorghum become raw material for bio brewing. So that's a closed loop of the circular economy. By using this way, we can reduce 50% of building areas, 50% conversion ratio, and 50% of labor cost by using builders' solution compared traditional insect breeding or rearing factory. So from waste to value chain restriction, that we need policy support, we need technology innovation, and need marketing acceptance. That's what we need in order to implement these values. For sure, there are a lot of social values. We can reduce pollution. We can have the resource recycling, reduce carbon emission, and economically we can lower processing cost increase value-added potential, and create new industrial. And also for the people, we have food more confident for food safety and the industrial innovation and create the new jobs. And for the players or company value, we have direct benefit, we have technical advantage and cost of optimization and good branding by using these upcycling solutions. That's all my presentation for today's. Any comments or questions are welcome. Thank you.
Okay. We will now open a space for questions and answers. We will share also the emails of the participants if you want to write the question, but we have now an open space at time for making questions to the speakers who are present now in this webinar. Engineer Viñar, please.
Yes, I don't know who can answer, but if it is possible to know what percentage of biodegradable packaging is used in the food industry in China. What percentage of the food packaging is biodegradable?
I don't know if anyone can answer this question. If not, we can send the question to the panel. I don't know if now is present.
Sorry.
Yes.
I want to check this question. This is for which person? This question? Because we have 4 speakers, and just now you gave a question, and this is for which person?
I think the first speaker talked about biodegradable packaging.
Yes.
Okay.
You can
Professor,
share the email.
Professor Yao, if you can give an answer for this question. Okay, maybe later we can give you the question by email. Yeah.
Yes,
Okay.
Very well.
we can mail the question.
Okay.
Is there another question? Dr. Celina Bernal is not present here because she has a severe familiar problem, so she has to travel. But if somebody wants to ask her something, we can write an email because she's not present here in the webinar. Yes, please.
I hear about the presentation about the data, and we can use for detoxing in water pollution.
We are sorry, but we cannot hear your
声音
question.
有点问题，高老师。
Chitosan,
Yes.
you use it for water pollution and the detoxing, the air pollution, the water pollution toxins. And I'm wondering whether the chitosan can use for mycotoxins absorbent.
We didn't test the use of chitosan for absorbing mycotoxins, but it would be interesting to make some work about this. But we are not working on mycotoxins.
And you use chitosan to absorb harmful compounds, right? And how to remove the chitosan after they absorbed the harmful compound from the water?
We separate the chitosan particles because we synthesize particles of different sizes, and we put them in a column, and these particles are separated.
So you're using a column.
We can reuse them. We can use them in several cycles. Recycling.
Okay.
Yes. And we tested also the presence of other ions in the system that can interfere with the absorption process. In each study, we analyzed the possibility of interference of other ions in the absorption process.
If the chitosan was used up, how to treat them? You just burn them out, or how to treat the used chitosan?
I don't hear. Sorry, I don't hear your question or comment.
If the chitosan was used up, how to treat the used chitosan?
How to? Sorry.
How to treat?
To treat?
Yes, you throw them away or burn them up.
I don't know, but we can remove from the chitosan the absorbed substance by acid or alkali treatment. We can remove the absorbed substance and we can use them again.
Okay, so it's recycling and acid treating.
Okay.
Thank you.
Is there any question?
I have no question, but I just a quick search, use some AI, and the answer for the bio-based plastic food usage now is only 30% in China. Annually, we manufacture around 162 million, no, 1.6 million tons of bio-based plastic, and the food package will be 25 million, so that's around 2.9%. That's the ratio for use the bio-based plastic for food package.
9%.
No, 2.9, around
2.9. Okay.
3%.
So it's a very early stage.
In Argentina, it's also very low, the percentage. Is there another question, please? I think that the webinar was very interesting with different subjects related to sustainability, with talks about science, technology, and also the participation of the industry, the innovative Chinese industry. So I think it was very useful for all the participants. So if there are no questions, I would like to sincerely thank the speakers for their insightful presentations and for sharing their expertise with us today, because the contributions have added great value to this webinar, and we truly appreciate the time and the effort you dedicated to preparing and presenting these lectures. We thank all the participants, and we look forward to welcoming you at the future webinar that will be next year, and we need time to organize this new webinar. I think we have very positive results from this joint project, and we will continue with this. It is important to share our emails in order to send our questions to the participants. And thank you very much again. Okay.
Thank you.
Bye.
Have a nice day.
Thank
Bye.
you.
Bye.
Thank you all. Bye.
Bye-bye.
Thank you. Please share the emails.
Yes.
Thank you.
Bye.
Thank you, Noemí. Congratulations.
Gracias.
Thank you.